Software Engineering Radio, episode 101, Debugging with Andreas Zeller. This is Software Engineering Radio, the podcast for professional developers, on the web at se-radio.net. SE Radio brings you relevant and detailed discussions and interviews on software engineering topics every 10 days. Thanks to our audience and the partners listed on our website for supporting the podcast. Hello everybody, welcome to this new episode of Software Engineering Radio in the new century, episode 101. This one is about debugging and specifically Delta debugging with Andreas Zeller from Saarland University. But before we get started, we have to make a somewhat sad announcement. It's about the SE Radio get-together. We have only received 6 or 7 position papers amounting to like 10 or 12 or maybe 15 people, and that's far too low to organize the get-together. The deadline for the papers was June 1st, and I've messed something up, so I said in the podcast June 15th, so we waited until June 15th, but still we didn't get any additional papers, so we had to cancel. So I guess SE Radio will stay a virtual endeavor without meeting in person. So sad but true. Well, let's get on with the episode. As I said, this one is about debugging, Delta debugging, with Andreas Zeller. Have fun. So welcome, Andreas, to the show.
Welcome.
So why don't you introduce yourself to our listeners?
I'm a professor at Saarland University, which has a very good computer science department, and I've been there for 6 years now. And before that, I did my PhD. I did a typical academic career with a strong practical side and especially debugging.
Okay. And the reason I found out about you was, actually that's not true. I read this beautiful code book, and there is a chapter of yours on beautiful debugging. But I also heard about Delta debugging before. So that's one angle to it. So before we discuss your specific thing, which is this Delta debugging stuff, let's discuss debugging in general a little bit. So what is debugging?
Debugging is the action of finding the defect that causes a specific failure. That is, your program crashes and you want to figure out why it failed, and you want to fix the program such that the failure no longer occurs.
And okay, yeah, that's a very general definition, of course. And by the way, we've recently had this episode with Bob Hanmer, who talked about fault-tolerant systems, and he explained the terms like fault, failure, error, and how one leads to the other. So we're now trying to find the root cause, not the final problem.
Yes, it's a long series of errors. So first, sometimes the programmer makes an error. This results in an error in the code. This then, when being executed, may result in an error in the program state. And this then results in an error in the program result. And all these errors have distinct names. So the error of the programmer is called a mistake. The error in the code is called a fault or a defect. In the state, it's called an infection. And when when you see it, the error in the program execution, that's when it's called a failure.
Right, so the final thing at the end of the chain is the failure.
Yes.
Yeah. Okay, so let's look a little bit about how debugging works in principle. I mean, there is always the problem that you have some kind of tool that you use to inspect, and the program needs to tell the tool where it is, or these kind of things.
Well, according to Somerville, debugging is totally trivial. Somerville has written a nice book on software engineering. It's for beginners. Mm-hmm. And he explains the debugging process in 4 steps. First, you locate the error. Then you design a repair for the error. Then you test the repair. This is essentially what you have to do. Of course, the first thing is how to locate the error, which is by far the most complicated thing of all.
Right, exactly. So that's something where tools are obviously used, as we all know.
This is right, yes, but the tools we're using the typical interactive debuggers, I'm afraid to say, are not really adequate for the kind of tasks debuggers have to do. In particular, because ordinary interactive debuggers in terms of their language, the way you interact with the program, you set breakpoints, you execute stuff. This is very, very low level, and there's virtually no way you can reason backwards, which is the typical way of reasoning when you're debugging. Mm-hmm. So the program has to be executed forward, but you have to reason backward in order to understand it.
Very good point. Yeah, didn't think of that before. One last thing before we go to the core of the discussion. I work quite a bit in model-driven development, so the question is always, how do you debug models? And one thing that comes up as well, in the generated code, you have to put in some callbacks. So in order for debugging to work, I guess always need some what's called debug information in the binary or whatever kind of thing you want to debug.
When you want to do interactive debugging, you indeed need to have a relationship between your original source code and the state you're seeing on the screen. When you're doing model-driven development, one needs to carry that relationship further up to the model.
Right.
And I'm not sure how much this is supported by current model-driven development tools.
Sure, I mean that varies, and in the worst case you have to build it yourself. But the point there is you have to somehow instrument the programs to make it debuggable. If you want to do interactive debugging.
If you want to do interactive debugging, you have to find a way to interrupt the program execution and observe the state, and to observe the state at some higher level of abstraction that is not as a series of bits and bytes spread across the memory, but of course to see the objects in the very same way that you originally defined them in your model or in your source code.
Right. So we kind of distinguish between debugging and interactive debugging. What other debugging techniques are there? I would guess that 90% of our listeners only know, this nice little tool where you can step through stuff, which is then called interactive debugging.
That's right. And this used to be the state of the art until, say, 10 years ago. However, there's a very nice set of tools and techniques available right now that automate most of the debugging, that automatically point you to locations where the error is most likely to be, that automatically identify causes of the failure in terms of program input, in terms of program state, or in terms of changes to the program code. You see, debugging is essentially a search process, which makes it different from all other software engineering activities, where you essentially construct something. When you construct something, you can plan how long it will take, more or less. However, when you're debugging, since this is a search process, it can take you any time between 5 minutes, 5 hours, or 5 days, maybe even 5 weeks to find a single bug. And this lack of being able to plan how long it will take is the major risk about debugging, because you never know when it's going to end. And this is also why programmers spend nights after nights chasing bugs and not coming home to their families and missing their social lives, which is why debugging is definitely an area which is in great need to be automated as much as possible.
Okay, but instead of automating, one thing would also be to make it a little bit more systematic. So you have this thing, the scientific method and systematic debugging. What is the scientific method and how does that relate to debugging? Or does it maybe not?
Well, most programmers I know, and I think I'm not that much of an exception, immediately jump to the interactive debugger as soon as you see a failure. And then you poke around, you step forward, step backward, poke in different directions. You can do this for maybe 5 minutes or so. If you haven't found anything, then it's time to step back from the computer. It's also time to step back from the interactive debugger and actually think. This means that you have to be explicit. To start with, how does the failure manifest itself? Why is this wrong? And simply stating this, simply writing this up on a piece of paper or telling to a friend already solves 2/3 of all debugging problems.
Sure, that's the dog debugging. So you explain the problem to your dog who sits next to you and suddenly you know what the problem is and you find the bug.
Exactly. That's the first thing. You need to be explicit when you're debugging.
Yes.
The next thing is, once you're explicit about the problem, you can think about possible problem causes. And these problem causes, of course, also have to be written down in some explicit way. The scientific method tells you the cause for a specific observation in nature typically, but this is not so much different from debugging, because as soon as you're debugging, your program becomes part of some inexplicable phenomenon, which is very much the same as in nature too. So you can apply the same techniques. So you come up with a hypothesis, and then you need to design a way to test your hypothesis. And you make an experiment, and depending on the outcome of the experiment, you refine your hypothesis or you reject your hypothesis. Mm-hmm. And this process can be followed pretty systematically, again, by being explicit, writing down what you think the hypothesis is, writing down the experiment, writing down the result. This seems somewhat tedious at first, but if you think about that, by writing that down, you can interrupt your debugging process anytime, come back next morning with a fresh mind. You really save time on that. And this is simply a systematic process, trying out stuff systematically rather than poke around and examining what other great stuff the program is doing, but which has nothing to do with the error you're looking at.
Yeah, exactly. So that's kind of a smart approach to debugging, and one could say that considering debugging as a search problem is more like a brute force attack. So what does it mean to consider debugging a search problem?
Essentially, this means that you have various search domains in which you're searching for causes. For instance, this is a nice story to tell. When the first versions of the Mozilla browser were released, this was in 2001, the Mozilla team had lots and lots of trouble with bug reports. They had plenty of bug reports, but they had no way to find out what was the relevant part of each bug report. Mm-hmm. So essentially the bug report said, I'm loading this web page and I'm printing it out and it doesn't work. But the web page in question would have thousands and thousands of lines, and you wondered, well, not everything on this web page will be relevant for making the program fail.
Yep.
So what they did actually, they called for volunteers on the net, for volunteers that would help them simplify these bug reports. And they actually gave out prizes such as stuffed gecko animals, the little green dragon that would be the mascot of the Mozilla team, and teams and T-shirts signed by the entire team and all. And within hours, they had dozens and dozens of volunteers and of simplified bug reports, which is very nice. But on the other hand, simplifying such a bug report is a very, very straightforward thing. You don't need to be a programmer to do that. What you do is you take the input, take half of the input, see whether it works, whether the failure is still reproduced.
Yes.
If it works, you do another half of the input. This is the scientific method at its easiest. You simply reduce the search space and go along until you eventually narrow that down to a very, very tiny input.
Okay. So this is basically what brought you to the delta debugging idea, right?
Exactly. So I was totally amazed at that, how you could have all these volunteers do that manually, which is so stupid. Well, it could have been done by monkeys, for instance.
Yeah, sure.
And well, they actually called for volunteers who didn't have any clue about. It actually advertised the whole thing. You don't have to have any programming knowledge. Basic HTML knowledge suffices. Yeah. I said, well, if this is so easy, I can just as well automate it.
Sure. Yes.
And the idea is that as soon as you have an automated test that checks whether a specific failure is still there or not, all you need in this case is a strategy that does this minimization for you, cutting away half of the input, see whether it still works, and cutting away other parts. The systematic cutting down of inputs and repeating and repeating again the automated test until you come up with a very, very simple input that produces the test. And this was the beginning of delta debugging.
Mm-hmm. That's also where the name delta comes from, where you change the input by increments or deltas.
Exactly. There's two explanations to the name. One is the delta that you apply to the input. The other one, this is a variant of delta debugging, which tries to find a minimal difference between two inputs. And this difference is a delta.
Yeah, there's one important thing you mentioned kind of on the side, which is kind of essential. You need an automated test. You need something that determines automatically whether the failure in that sense still manifests itself or not. So that's actually an interesting relationship to test-driven and all this test hype. Well, I shouldn't call it hype. To the justified idea of making test an essential part of software development.
This is totally right. So in test-driven development, you do have two distinct benefits from writing your tests. First thing is your test serves as a specification. The second thing is your test can later on be run in order to protect you from change impacts you don't want to.
Yep.
Now you get a third benefit. That is, as soon as you have an automated test, you also have automated debugging in the sense that you can automatically be brought to cause of the failure.
Is that, I'm kind of diverging a bit, but is that also a technique that some of the automatic test generation, test coverage tools like Agitator or Agitar? I don't know which one. You know what I mean? Do they use this kind of stuff too? Is that related?
These techniques can be very easily combined with automatic test generation, and I'll be visiting Agitar in March in order to talk about that.
Okay. Let's look at this delta debugging a little bit closer. The example you gave initially, the manual delta debugging by the Mozilla folks, was basically changing the input to the program being more or less the HTML renderer, and the program, the HTML page. So in that case, you actually debugged a problem in program input.
Yes.
What else can you debug? Because typically, if I consider debugging, I'm not trying to debug the program input.
This very much depends on how much your input points you to specific places in your program. In case of Mozilla, for instance, we eventually found out that printing a select tag, for instance, in HTML, caused the browser to crash. And of course, there's one specific place in the program where these select tags are handled. So this can be very, very useful. Also think about random tests. For instance, you're testing a SQL server, for instance, and so you're generating large SQL queries that cause your SQL server to produce wrong results. Now, if you come to a SQL vendor and tell them, hey, here's my 30-line nested SQL whatsoever command, and it crashes, and the vendor will tell you, well, that's not on our priority list because nobody ever does such queries. Yeah. But if you minimize that, say, to a 2-line thing, and these 2 lines still produce the failure, the vendor will become very, very upset, because not only do you have a means to point people to the error, but you can also easily generalize. You can characterize the error, you can identify duplicates, and all this happens when you're dealing with input.
Right, so this is actually exactly the point where you try to narrow down a test case so everybody knows precisely what the problem is.
Exactly. Once we did this for input, however, we were also thinking about other applications, and one interesting application is doing this for changes. So
changes of what?
Changes to your program code.
Okay.
So think about the version history, or think about a very simple example. Your computer still worked yesterday, and now you're applying some patches, some changes to your system, and suddenly it doesn't work anymore. Yeah. And you wonder, why did that happen? And as soon as you have an old version of your program that worked, in which a test worked, and now you have a new version in which a test no longer works, you can again apply delta debugging in order to figure out what the subset of these changes it was that actually caused the failure.
So in this case, you debug the program structure, which is more or less the classical case of debugging that most people know best, I guess.
Exactly. In that case, we're actually dealing with the program code and we're making changes to the program code. It's actually pretty funny to see that if you apply just a subset of changes, you get pretty weird programs out of that in cases. It's also advisable to run this in a sandbox. And this is definitely something that would be extremely tedious to do manually. Yeah, sure. So this is where automation fully plays the game. Yeah. And we realized that for a German company called Web.de, who are deep in the integration of different open source programs.
Yeah, actually, I work for them.
You work for them, cool.
As a consultant, so I know them very well.
Okay. So we did this for them, and initially our plan was to make this an Eclipse plugin with what we called one-click debugging. Yeah. So your unit test fails, and our plugin would automatically record all the results of the unit test, and if it would find that some earlier configuration existed in which this very unit test worked, then it would automatically narrow down the change.
Nice.
And after a couple of minutes, these processes are not really fast. After a couple of minutes, it would automatically identify the change that led to the failure. Actually, the people at Web.de call this the blame-o-meter because it would immediately point people to the change that made the program fail. But unfortunately, our idea of one-click debugging didn't turn out well. So because it turned out that we didn't even need that one click, so we made this zero-click debugging. As soon as a JUnit test would fail, in the background, our plugin would automatically set itself into motion and isolate the failure-inducing change.
So it means that what you did is whenever you checked in something, you also checked in the JUnit results, so you could compare that to different. What was the granularity of the changes you did? Was it the local history, or was it like the change in CVS or wherever?
Well, when I first implemented this was all a set of scripts, and it only worked on the CVS history. But when my student Martin Burger did that for web.de, he actually also took the local history into account.
Very nice.
And so we were able to really narrow that down. This also works when you're doing manual work. So suppose you work in the morning, some test works, you're doing a couple of changes, no longer works, and all of a sudden, and after a couple of minutes, or in that case seconds, a little dialogue pops up and tells you this is the place and this is the change. My student actually also inserted a dialogue that allowed you to revert this change such that the failure in question no longer occurred. We are still discussing whether this is a good idea because, reverting the change will make the failure go away, but this will not necessarily result in a complete correction of the program.
Because you don't have 100% coverage. Essentially.
No, because simply applying this change may make this failure go away, but it may cause other failures later on in the program.
Yeah, but that means that other tests would fail if you had 100% coverage. Which
if I had 100% coverage, yes. But my idea was always, the programmer is the last one to take responsibility of the code, so it should be the programmer who actually applies the change.
So I have a couple of follow-on questions to that, but let's first look at the third aspect, which is to debug program state. That's, for me, the most abstract to understand. So what's that?
This was a pretty weird story. The thing is that if you look at input, you can isolate input that caused the program to fail. So far, so good. But input does not always point you to the right location in the code, because input is processed all along the execution of the program. Think about a compiler, for instance. You have some input, say a plus sign or whatsoever, and this gets processed all along the entire chain of optimizations that happen within the compiler code generation and all. So it would be very, very difficult to, even if you know that some part of the input causes the failure, to locate a specific place within the compiler. So you actually have to go and decompose the execution of the program into individual steps, where each step takes input from the previous component. Think of a pipeline, for instance. And then you can see a program execution as a series of program states. So the very first component takes the input, produces a state. The next component takes a state, produces another state, and so on until the final state is being, displayed to the user or written to a file or whatever. So you see the program execution as a series of states. And once you do that, you can also narrow down differences in state that cause the program to fail.
Okay. And how do you actually track that state? I mean, that sounds to me like a pretty abstract concept.
It is both a very abstract concept, but it's also full of technicalities. So we implemented a tool that would extract the state from actual executions. We would do so by instrumenting an ordinary debugger. We would look at all the variables, take their values, and if it's a pointer, we expand the appropriate data structures until we arrive at a fixed point. So we'd actually extract all the accessible variables, including everything on the heap, in the stack, and so on, with all their values. And once you have such a state, you can also manipulate it, as you can do in ordinary debuggers just as well. And if you have two states, for instance, a state from a passing run, where the test passes, and a state from a failing run, where the test fails, you can go for a diff between these two states. This is somewhat complicated because the state is essentially a graph. And so you have to look for diffs within graphs, but this is also something that can be solved. And now you have differences between these states, and if you have a state from a passing run and a state from a failing run, you know that the difference between these two states is the difference that caused the program to fail. And so the next idea is, once you have these differences, you need to narrow down these differences again in order to point to the state that makes the program fail.
You talked about this web.de stuff. On the other hand side, in your chapter for the book, you talked about delta debugging being a prototype problem because it kind of doesn't scale to big problems, or because it's too slow, because it's essentially brute force. So how realistic is it? How much practical use is there? Where's the tool I can download? Is that the essential question, I guess?
In terms of input, there's a tool called Delta from Berkeley which you can download, but the algorithm is so simple.
That's actually true, yes.
It fits on in 20 lines of Python code. So for input, you can easily implement this yourself, and by the same way adapt it to your code. And it's being used in many, many places, including at Microsoft, at SAP. Whenever you're doing something, it's so easy to implement. It's straightforward.
So the notion that it's a prototype problem isn't. Did I get this wrong, or what? I mean, I think it does say it in the paper.
It depends on what you're applying this to. You're applying this to input. It's so straightforward.
Okay.
You can just implement it.
I see.
You implement it on changes. There we actually have a plugin to download called DD Change. You can download this for Eclipse and make it work immediately. If you apply this to a program state, however, this is very fragile and experimental. This is not something I would recommend for general use.
Okay. And the search algorithm you're using here, is it like, I mean, I was thinking about using, I don't know, genetic algorithms that you actually don't, do the changes systematically and therefore increase the speed of the search. Is that something you're playing with, or is it really just basically narrowing down half, like first taking this half and that half and then taking the half that works and so on?
Well, when I designed this whole thing, I actually looked very hard into appropriate genetic algorithms and search algorithms, but wouldn't find anything that fit. So what the delta debugging algorithm actually is, you can see it as a binary search. This is the base of the whole thing, first half, second half. Yeah. But it comes with a twist. If neither the first half nor the second half lead to result, for instance, you want to minimize things, neither the first half of the input works nor the second half of the input works, then comes a specific twist. Rather than splitting the input in 2 parts, it splits it in 4 parts, 8 parts, or the other way around. It doesn't take away the first half, but takes away the first quarter, second quarter, third quarter, and so on. And then it takes away the first 8, then the second 8. And by taking away smaller and smaller pieces of the input, it's able to it's able to narrow down the input pretty quickly still, but without going through the hassle of taking away, say, single characters from the very beginning, which would be a very, very tedious search.
Yeah, okay. I mentioned already before, we talked about this relationship to testing, because you can't do delta debugging if you don't have a test that automatically verifies the point, the error. And I had this question here in my script that talks about what's the relationship to testing, because some people say you don't need to debug if you have enough unit tests, or if you do test-driven development, the need for debugging goes down. So, I mean, that's not necessarily. I mean, the kind of debugging you propose isn't debugging in the sense everybody does. So it's more like a systematic exercise of the tests you have. So the point is, is there anything more to say on the relationship between test-driven development and delta debugging?
Definitely, because what techniques like delta debugging do, they give you causes, but they do not necessarily give you errors. In order to define that something is an error, you need a specification. Yeah. That is, you need, for instance, unit tests, assertions in your code. Yeah. Contract-driven development, say like in the Eiffel programming language, is a very good example for that. And essentially, the more checks you have in your code that check whether something is an error or not, the easier it is to detect errors, and also the easier it is to locate the error. If you have a function in which the pre- and post-conditions are clearly defined and checked, the preconditions are all satisfied, the post-condition is violated, then you definitely know, well, the error is in that very function. Yeah. And therefore, this is, of course, another way to automate debugging. The more tests you have and the more assertions you have in your code, the easier your debugging life will be.
Yeah, absolutely. Okay, so to wrap this up, let's discuss a little bit other approaches to automatic program. Well, I shouldn't say maybe other approaches to automatic program verification, but your approach is certainly a way to help you automate some aspect of verifying that a program works, and then if it doesn't work, why? So is there any relationship to static analysis tools and some of these things?
Yes, of course, because a static analysis tool will definitely rule out a number of possibilities. And a static analysis tool will tell you, for instance, during debugging, that there are places which simply cannot have any influence. Yeah. So static analysis can come in very handy in places. And the second thing is, of course, that static analysis tools are great tools for detecting potential errors, such as here's a potential overflow, or here's a potential loop that never ends. Yeah. And like stuff.
Okay. So, but there isn't any specific collaboration, because when you talked about program state, when we did the episode on static analysis, that's also a term that came up, because, of course, a static analysis tool has to try to understand the program and abstract the program state to meaningful, not just a bunch of variables, but to a meaningful state that, so that sounded like there is a relationship there.
Oh, there's a group of Neelam Gupta in Arizona, for instance, who has combined delta debugging techniques with static and dynamic analysis techniques, and And they've been very successful, in particular, combining multiple approaches such as program analysis and these experimental approaches, search processes and delta debugging, is one of the most promising ways to even to improve the accuracy and the speed of these techniques even further.
So we talked about delta debugging as a way of automating some of the tedious tasks of manually finding an error. Is there other approaches maybe you're working on today or that you've worked on in the past or you know about that kind of automate that and help people get rid of some of the tedious aspects of debugging?
The general idea of the work we're doing right now is to exploit all the information there is from program runs and from program development. You see, in delta debugging, we look at the changes, we looked at the automated test error, we look at the code, we look at the program state, and there's so much more to exploit and which is recorded in daily process, such as, for instance, bug reports, the change history, profiles of how the software is being used, emails between developers, models, you already mentioned that. Yep. And all this is being recorded in appropriate databases, and what we're doing is we mine these databases, for instance, to figure out where in your program the most bugs occurred in the past. This is obviously information you can use for debugging because you can focus on the usual suspects. Yeah. But this is also information that can be very relevant for managers, for instance, when you're deciding where to test most, because you focus on those places where the most bugs are. And you can use that to identify patterns that in your program, structures in your program that typically correlate with a higher risk of making mistakes. And once you bring that to some sort of a climax, you end up in tools that assist you while you're programming and that tell you this is something that looks like something that should be tested more because from history we know that this structure results in many bugs. Yep. Or this is the way of interacting with a module that others haven't done before. So maybe you'd look at some other code examples. And of course, during debugging, these are places I would look at first because these are the most likely places to contain the bug. So our long-term vision in, say, 10 or 20 years from now is to have some sort of your program environment acting as a buddy while you're programming, as an assistant while you're programming. Think of it like a navigation system that tells you where you are, where you should go, that tells you when you leave the track, and that also tells you how long it will take you to get there.
Cool. So I think we're nearing the end of the show. So is there anything else I should have asked? Anything else you want to say?
I think my idea is that no programmer should get home late because he or she has been debugging. So my idea is, at the end of the day, press a button, you look at your notes, go home, come back the next morning with a fresh mind. Your computer is there to do the tedious tasks. Sure. It's not you. So let your computer do all the hard work.
So in some sense, it's a continuation of the trends we've seen before. We have automated builds, we have automated test execution, we have, in at least some environments, automatic code generation from more semantic high-level models. So automatic debugging sounds like another building block in that next step of automating software development.
Yes, eventually our keyboards will have just one single button. This is the do what I mean button. The only thing is that I suspect that there's going to be a second button, which is do what I really mean. And,
do what I should have meant.
Do what I should have meant. We're not there yet, but at least let's take some of these tedious tasks away from the program and move them over to the machine.
Okay, thank you, Andreas, very much for being on the show.
Thank you.
Thanks for listening to Software Engineering Radio. If you want more information about the podcast and all the other episodes, visit our website at se-radio.net. If you want to support us, you can donate to the SE Radio team via the website, or you can advertise for SE Radio, for example, by clicking on the Dig, Reddit, Delicious and Slashdot buttons. To contact the team, please send email to team@seradio.net, or if it's specific to an episode, please use the comments facility on the website so other people can read and react to your comments. This episode of Software Engineering Radio, as well as all other episodes, are licensed under a Creative Commons license. Please see the website for details. Thanks to Charlie Crow and the PodSafe Music Network for the music used in this show. The song is called Vegas Hard Rock Shuffle.